So today we can go to lesson 7, the last lesson of this semester, Dispersion Management. Okay. There are 4 sections in this lesson, starting with material dispersion. Okay. You have studied some of the materials in lesson 3. When we talk about light-matter interaction, we treated material dispersion there. Okay. Then it's something new, temporal dispersion based on angular dispersion. This is something new, angular dispersion. We will define what is angular dispersion and why is it related to the temporal chirp that we have been familiar with. Then in section 7-3, we will talk about grating pairs. This is a traditional pulse compressor used in dispersion compensation. Okay, it's still used today. Okay, and usually you can create a very large compression ratio or stretching ratio by using grating pairs. Previously, we spent the last section about prism pairs, but in view of the tendency that chirp mirrors become more and more popular instead of prism pairs, so I replaced the last section by chirp mirrors, which is a very different geometry. Okay, it can provide dispersion compensation, but with very different geometry. Okay. So let's start with material dispersion, including material dispersion formalism and properties. Okay, I believe you must have been familiar with this picture. GDD-induced spectral phase modulation. Assume we have a transform-limited input pulse. So in the time domain, you have an electric field like this. Fringe density is nearly constant. And this is frequency domain picture. The blue curve is the power spectrum. The red dashed line means the spectral phase. Since this is a transform-limited pulse, so your spectral phase is a constant function. Okay. After the pulse passes through a dispersive medium, this is the output pulse. We know in the time domain, the pulse will be stretched and becomes chirped. So the fringe density varies with time. In this example, fringe density increases with time. So this is an up-chirped pulse, assuming the medium is normally dispersive. How about the frequency domain? The blue curve does not change. The power spectrum is the same. But you will have maybe parabolic function for your spectral phase because different colors propagate at different speeds. So accumulated phase will be different, frequency dependent. Okay, so that's why you have a stretched and a chirped pulse in the time domain. Okay. So the picture is about qualitative description. How about quantitative analysis? This is the only formula we need. The corresponding spectral phase modulation, say it's designated by psi of omega, equals minus beta of omega times L. L is the thickness of the medium. Okay, it is a constant. How about beta of omega? We know it means propagation constant of the medium, which is usually formulated in this way. Okay, omega times index of refraction over light speed in vacuum, c. Okay, basically it's index times wave number in vacuum, omega over c. Okay. And then you can identify beta of omega is actually a nonlinear function of omega as long as your medium is dispersive. What is the meaning? the medium is dispersive. It means n of omega is a function of frequency. And you have omega already there, so their product must be nonlinear as long as n is not a constant. It's a dispersive medium, you got a nonlinear function of beta. And this formula tells us if you have nonlinear function of beta, you have nonlinear spectral phase modulation, starting with second order function, parabolic function. You can have higher order terms, of course. If we restrict ourselves to third order approximation, the spectral phase modulation function can be represented by second order contribution proportional to omega squared, and the third order contribution proportional to omega cubic, where these two coefficients, psi 2 and the psi 3, are related to beta 2, beta 3 in these two ways. Okay, so basically proportional to thickness. Okay. And in this slide, I try to demonstrate the dispersion formulas both in variables omega and the variable lambda. Okay? The relation between omega and the lambda is shown here. Okay? Omega is angular frequency, which is 2 pi times non-angular frequency f, or nu, right? And we also know the formula. Frequency f equals light speed c over wavelength lambda. So omega and the lambda actually are related in this nonlinear relation. Okay. So if you take first order derivative, what can you have? If you check this formula and performing first order derivative with respect to lambda, okay, so you have d omega over d lambda to the left-hand side. How about the right-hand side? Derivative with respect to lambda. 2 pi c is just the constant, so you are actually calculating 1 over lambda derivative, which is minus lambda squared, something like that. But by taking inverse, you got d lambda over d omega equals this one, minus lambda squared over 2 pi c constant. We will use this relation later. Okay? Then let's see what is the relation of between n prime of omega and n prime lambda. The definitions are, this is first order derivative of index of refraction with respect to variable omega. And this is derivative with respect to variable lambda. They are different, right? So you can use chain rule, okay? 只是利用这个 picture， 也就是highly trapose 它的宽度的公式，你可以推导出另外一个 GVD 参数 big D， 它跟 beta 2之间的关系啊。那 beta 2的 formula 有 ，big D 的 formula 就跟着有啊。反正它们都是跟折射率的二次微分有关。